Welcome to the 9th program on electromagnetics and the second program on magnetostatics. In the previous program, we had talked about the basic laws and techniques of determining magnetic field due to a current carrying conductor. Now we are in a position to determine the force which a magnetic field exerts on a current carrying element or a loop or on a charged particle. This study is very important in understanding various devices like voltmeters, ammeters, cyclotrons, MHD generators and so on. In this program, we will be talking about these forces. Thereafter, we will talk about the magnetic torque and moment, and finally, we will be talking about the magnetic dipole. Now, coming to the forces due to magnetic fields. The force exerted by a magnetic field can be due to three reasons. The first is due to a moving charged particle in a magnetic field, on a current carrying element in an external magnetic field, and between two current carrying elements. Now, the force on a charged particle. In an earlier program, it was discussed that the electric force Fe on a stationary or moving charged particle Q was given by Coulomb's law and is related to the electric field as Fe is equal to Q into E. It can be noted that Fe is independent of the velocity of the charged particle and it performs work on the charged particle and it also changes its kinetic energy. While on the other hand, a magnetic field can exert force only on a moving charge. From experiments, it is found that the magnetic force Fm exerted by a charged particle Q moving with velocity u and in a magnetic field B is given by Fm is equal to Q u cross B. Here it can be seen that the force is perpendicular to both the velocity of the particle and the magnetic field B. Now, Fm cannot perform any work because it is at right angles to the direction of the motion of the charge, that is Fm dot dl is equal to 0. Because of this, Fm cannot change the kinetic energy of the particle. Also, Fm is usually less than Fe except at high velocities. For a moving charge Q in both the electric and magnetic fields, the force experienced is given by F is equal to Fe, the electric force, plus Fm, the magnetic force, which is equal to Qe plus Q u cross B, which is equal to E plus u cross B. This is known as the Lorentz force equation, which relates mechanical force to the electric force. If the mass of the charged particle moving in the electric and magnetic field is m, then by Newton's second law of motion, F is equal to ma, which is equal to m du by dt q into E plus u cross B. The solution to this equation is important in determining the motion of charged particles in the presence of both the electric and magnetic fields. However, it should be noted that under such condition, the energy transfer is only by means of electric field. The table 9.1 shows the force on a charged particle under stationary and moving condition. When the charged particle is stationary, then the force experienced by it is equal to Q into E, while if the charged particle is moving, then the force experienced by it would be equal to Qe plus Q u cross B, which is equal to Q E plus u cross B. Next, we come to the force on a current element. To determine the force on a current element IDL of a current carrying conductor due to a magnetic field B, we modify equation 9.2, that is Fm is equal to Q u cross B, using the fact that for convection current J is equal to rho v into u. We had talked about this in the third program. Also in the earlier program, we had discussed the relationship between the current elements, that is IDL is equal to KdS is equal to JdV. Combining equation 9.5 and 9.6, we get IDL is equal to JdV is equal to rho v u dV and which is finally equal to dq into u. Thus, an elementary charge dq moving with velocity u is equivalent to a conduction current element IDL. Thus, the force on a current element IDL in a magnetic field B is found from equation 9.2, that is Fm is equal to q u cross B, by replacing qu by IDL, that is dF is equal to IDL cross B. If the current I is through the closed path L or the circuit, the force on the circuit is given by integrating F over the complete path to give equation 9.9. Now here it should be noted that the magnetic field produced by the current IDL does not exert force on the current element itself, just as a point charge does not exert force on itself. The B field or the magnetic field that exerts force on IDL must be due to another element. In other words, the magnetic field in equation 9.8 or 9.9 is external to the current element IDL. Now, instead of the line current IDL, we have the surface current KdS or the volume current JdV. Then equation 9.8 becomes dF is equal to KdS cross B or dF is equal to JdV cross B, and when we integrate it, we get the expressions for force. Now, from equation 9.8 we have dF is equal to IDL cross B, and from this we can define the magnetic field as the force per unit current element. Alternatively, B can also be defined as the vector that satisfies the equation Fm by Q is equal to U cross B, just as we define the electric field as the force per unit charge. From these two definitions of B, we can say that B represents the force properties of a magnetic field. Next we come to the force between two current elements. In the figure we can see two circuits, one carrying current I and the second carrying current I2. We take a small current element in each one of them. In the first circuit we take I1 dL1 and in the second we take I2 dL2, and let us find out the force exerted by one loop on the other. According to Biot-Savart law, both the current elements produce magnetic fields. So we may find the force d of dF1 on element I1 dL1 due to the field dB2 produced by the current element I2 dL2. Therefore, d of dF1 is equal to I1 dL1 cross dB2. Now, by Biot-Savart law, dB2 is given by equation 9.11, and when we put this value of dB2 in equation 9.10, we get the expression for d of dF1 as given by equation 9.12. If we take the integral of equation 9.12, we get the complete expression for force, that is force on the first circuit due to the current in the second circuit, and we get the expression given in 9.13. Similarly, the force F2 on loop 2 due to the magnetic field B1 due to loop 1 is obtained from equation 9.13 by simply replacing the subscripts. It can be shown that F1 is equal to minus of F2, showing that F1 and F2 both obey the Newton's third law, that action and reaction are equal and opposite. Next we come to the magnetic torque and moment. Now that we have considered the force on a current loop in a magnetic field, we are in a position to determine the torque on it. The concept of a current loop experiencing a torque in a magnetic field is extremely important in understanding the behavior of orbiting charged particles or DC motors or DC generators. If the loop is placed parallel to the magnetic field, then under such a condition, it will experience a force that would tend to rotate it. The torque on the loop is the vector product of F and the moment vector R, so that T is equal to R cross F. Let us apply this to a rectangular loop as shown in figure 9.2a. It can be seen that the sides CD and DA are parallel to the magnetic field, that is, the current element in this part, that is CD and BA, is parallel to B, and therefore no force is produced on them, and therefore force for the complete loop is given by equation 9.15, and we see that the net force is 0. That is, F naught on BC and F naught on DA are equal and opposite. Thus, no force is exerted on the loop as a whole. However, F naught and minus F naught act at different points on the loop, thus create a couple. If the normal to the plane of the loop makes an angle alpha with B, then the torque on the loop can be written as shown in equation 9.16, that is T is equal to B I LW sin alpha, where LW is nothing but the area of the loop given by S, or we can write T is equal to BIS sin alpha. We now introduce a quantity M known as dipole moment or the magnetic dipole moment given by IS into AN, where AN is a unit vector normal to the plane of the loop and whose direction is determined by the right hand rule. And therefore, we get the expression for T, which is equal to M cross B. Although the expression has been obtained for a rectangular loop, it is generally applicable in determining the torque on a planar loop of any shape. The only condition is the magnetic field must be constant and uniform. It should be noted that the torque is in the direction of the axis of rotation and is directed with the aim of reducing alpha so that B and M are in the same direction. Next, we come to the magnetic dipole. It is similar to the electric dipole that we had encountered while studying electrostatics. A bar magnet or a small current loop is usually referred to as a magnetic dipole. Here, we shall determine the magnetic field B at an observation point P whose coordinates are r, theta and phi, that is, it has spherical coordinate symmetry, due to a circular loop carrying current I. The vector magnetic potential at P is given by equation 9.20. From the figure, it can be seen that the radius A is very small in comparison to the distance r, and therefore for r much greater than A, the loop appears small at the observation point, and A has only the A phi component, and it is given by equation 9.21a. And on simplifying and putting the value of M, we get the expression 9.21b, which is A is equal to mu naught M cross AR upon 4 pi r square, where M is equal to I pi a square AZ, which is nothing but the magnetic moment of the loop, and AZ cross AR is equal to sin theta A phi. We can determine the magnetic flux density B from the equation B is equal to curl of A as B is equal to pi naught M upon 4 pi r cube into 2 cos theta AR plus sin theta A theta. The expression is similar to one which we had determined for the electrostatic case. It is interesting to compare equation 9.21 and 9.22 with similar expressions developed for dipoles for electric potential V and electric field intensity E in the case of electrostatics. The comparison is done in table 9.2, in which we see a striking similarity between magnetic flux density in the far field due to a small current loop and electric field intensity in the far field due to an electric dipole. It is therefore reasonable to regard a small current loop as a magnetic dipole. In table 9.2, there are two cases. The first is for a monopole and the second is for a dipole. For a monopole, the expression for V for the electrostatic case is Q upon 4 pi epsilon naught r, while that for electric field intensity is Q AR upon 4 pi epsilon naught r square. For the magnetostatic field, the concept of monopole does not exist. That is, a monopole cannot exist in isolation. However, for the second case, that is for a dipole, the expression for V in the electrostatic case is Q cos theta upon 4 pi epsilon naught r square, whereas that for the electric field intensity is Qd upon 4 pi epsilon naught r cube into 2 cos theta ar plus sin theta a theta. We have similar expressions for the vector magnetic potential A and the magnetic flux density B, as can be seen in the figure. Next, a short permanent magnetic bar shown in 9.4b may also be regarded as a magnetic dipole. It can be observed that the magnetic lines of force due to the bar are similar to those due to a small current loop. Consider the bar magnet shown in figure 9.4, where Qm is an isolated magnetic charge or the pole strength and L is the length of the bar. Then the dipole moment is given by Qm into L. When the bar is in a uniform magnetic field B, it experiences a torque given by equation 9.23, that is T is equal to m cross B is equal to Qm L cross B, where L points from south to north. The torque tends to align the bar with the external magnetic field. The force acting on the magnetic charge is given by F is equal to Qmb. Since both a small current loop and a bar magnet produce magnetic dipoles, they are equivalent if they produce the same torque in a given magnetic field, that is when T is equal to Qmlb is equal to Is into B. Hence we can say Qml is equal to Is, implying that both have the same dipole moment. Next we come to the magnetic boundary conditions. Magnetic boundary conditions are the conditions that magnetic field intensity H and magnetic flux density B must satisfy at the interface separating two magnetic media. The treatment is similar to what we have done in electrostatics. Here again we make use of two laws. The first is the Gauss's law for magnetic fields, which is B dot ds for the entire closed surface is equal to 0, and the second law is the Ampere's circuital law, that is H dot dl over the closed path is equal to the current enclosed equal to I. Now consider the boundary separating two magnetic media which have permeability of mu1 and mu2 respectively. As can be seen in figure, B1 can be decomposed into two components, B1t and B1n, the tangential and normal component respectively, and similarly B2 can be decomposed into two components, B2t and B2n, the tangential and normal component respectively. If we apply the first law, that is the Gauss's law for magnetic fields, that is B dot ds over the closed surface is equal to 0 for the Gaussian surface, which here is the pillbox. As can be seen, there are three surfaces to it: the top surface, the bottom surface and the cylindrical surface. On the cylindrical surface, B dot ds is equal to 0 because at any point the angle between B and the area at every point is equal to 90 degree, and therefore B dot ds over the entire pillbox is given by the equation shown at the bottom, which then on simplifying reduces to B1n is equal to B2n, or H1n into mu1 is equal to mu2 into H2n. This equation shows that the normal component of B is continuous at the boundary, while the normal component of H is discontinuous at the boundary. Again, if we apply equation, that is Ampere's circuital law, that is H dot dl over the closed path is equal to I over the closed path ABCDA, where surface current K on the boundary is assumed normal to the path, and on solving and keeping del H tending to 0, we get H1t minus H2t is equal to K, or B1t upon mu1 minus B2t upon mu2 is equal to K, or in most general form we can have H1 minus H2 cross AN12 is equal to K, where AN12 is a unit vector normal to the interface and directed from medium 1 to 2, If the boundary is free of any current, then in that case equation 9.31 reduces to H1t is equal to H2t or B1t upon mu1 is equal to B2t upon mu2. This shows that the tangential component of H is continuous at the boundary while the tangential component of B is discontinuous. Now, as again can be seen in figure 9.5a, B1 makes an angle of theta 1 with the normal while B2 makes an angle of theta 2 with the normal. Using equation 9.29, it can be seen that B1 cos theta 1 is equal to B2 cos theta 2. Again, from equation 9.34, it can be seen that B1 sin theta 1 upon mu 1 is equal to B2 sin theta 2 upon mu 2. If we divide equation 9.36 by equation 9.35, we get tan theta 1 upon tan theta 2 is equal to mu 1 upon mu 2, which is the law of refraction for magnetic flux at a boundary with no surface current. In this program, we have talked about the force exerted by a magnetic field on a charged particle, on a current element, and between two current carrying loops. We have also talked about the magnetic moment, and finally we talked about the magnetic dipole moment and the analogy between the electrostatic case and the magnetostatic case. I hope you have enjoyed this program. Thank you.